Okay, let's continue talking about the structural specificity of IR spectroscopy. When trying to determine the structure of a molecule using an IR spectrum, it's important to remember that largely this is used for hydrocarbons, which means carbon and hydrogen. And the first thing that we normally do is try to figure out, are there single bonds or double bonds, and what is the nature of the carbons and the hydrogens. But real functionality of organic molecules involves the incorporation of heteroatoms like oxygen. And oxygen makes up probably the largest group of organically important compounds. Because of that, we're going to start memorizing the names of and structures of oxygen-containing organic molecules. These break down into these 6 categories. The ether molecule is a molecule which has a carbon which is single bonded to an oxygen which is single bonded to another carbon. So if you just incorporate an oxygen into the carbon chain, it's referred to as an ether. An alcohol is a compound that also has a carbon-oxygen single bond, but also a hydrogen bound to that oxygen. That makes this a terminal group, because you can't stick anything more on the end of that hydrogen. Remember the rules of Lewis structures. If we go to a carbon that has a double bonded oxygen to it, then if it's just in the hydrocarbon, that is referred to as a ketone. That carbon-oxygen double bond is called the carbonyl. So if we have a carbonyl, a carbon double bonded to an oxygen, stuck in between a couple of carbons, then that's referred to as a ketone. An aldehyde is like a ketone in that it has the carbonyl, but instead of being between 2 carbons, one side has a hydrogen on it. Again, that means that this becomes a terminal group on the end of a molecule, because you can't stick anything more onto the hydrogen. Remember, in a Lewis structure, carbon gets 4 sticks, hydrogen only gets 1, and oxygen gets 2 in order to maintain a formal charge of 0. If we combine the carbonyl with an alcohol group, we all recognize that as the carboxylic acid. And finally, if we have the carbonyl with an ether, that group is called an ester. All right, there are 6 different classes of compounds here, but the good news is it's made up of components of only 3 stretches. The carbon-oxygen single bond, which we've already talked about, occurs at about 1200 reciprocal centimeters. Don't get too concerned about exact numbers here. This is not a spectral interpretation class, it's a recognition class. We have a carbon-oxygen double bond, which again we discussed in earlier videos, shows up at about 1700. And so the only thing we're adding on is the oxygen-hydrogen, which shows up at about 3400 reciprocal centimeters. Those 3 stretches are the major components of oxygen-containing molecules in an IR spectrum. Recognizing them is actually pretty easy. If we remember that the alcohol group shows up at 3,400 reciprocal centimeters, that's about here. The alcohol group is easy to recognize when it's in solution because the hydrogen bonding makes this peak very wide and very strong. This peak right here is the OH peak. We've already talked about the peak at 2,900 is the CH coming from a saturated system, and the peaks at 1,400 are the peaks coming from the CC single bond. But an alcohol has both the OH stretch and the CO stretch. So here's a pretty big peak down here at about 1,200. That corresponds to the CO. An alcohol has got to have both the CO at about 1,200 and the OH at about 3,400. If we go to an ether, really that's only going to have the CO single bond stretch at about 1,200 or so. If you look, there's no big peak here indicating that there is an alcohol. So we know there is no OH stretch in this molecule. We still have the CH stretch here and the CC single bond stretch here. And note, here is the big stretch of the C single bond O. Now if we go on to carbonyl containing compounds, remember the carbonyl is about 1,700 reciprocal centimeters, and it is a very easy peak to recognize. It's going to be a big, strong peak right at 1,700 reciprocal centimeters. That makes this the C double bond O peak. The two types of carbonyl containing compounds that I want to start with is first just the ketone, where like the ether, you just put the carbonyl in the middle of a carbon chain. So there's a carbon on both sides of it. That means the only peaks you're going to see is the carbonyl at 1,700 in this saturated system, CC single bond, and the CH. The more special case is the aldehyde. And the aldehyde, like a ketone, contains the carbonyl, but instead of having a carbon on both sides, it has a hydrogen, which makes the aldehyde the terminal group. Here is the big, strong peak at 1,700, which is the C double bond O. And we have saturated carbon-hydrogen stretching going on. But this particular CH stretch is a special CH stretch because it's not the same as an unsaturated stretch, but it's not the same as a saturated stretch. And it creates what is referred to as a Fermi doublet. It will show a peak at 2,700 reciprocal centimeters. An aldehyde will show a unique peak at 2,700 reciprocal centimeters, which can clearly identify this compound as not just a ketone. This peak right here means that it's an aldehyde. Other oxygen-containing compounds and carbonyls are combinations of both the C double bond O and the C single bond O. Of course, we recognize this as a carboxylic acid, but really that's just the combination of this at 1700 and that and that. So we have the C double bond O, we have the C single bond O, and we have the OH. The carbonyl is the big peak at 1700. The C single bond O, we can assign that somewhere in here, even though resonance is going to make that a little stranger. But then, most importantly, we're going to see this OH stretch. And that OH stretch is now extremely broad, because that OH, that H, can be resonantly distributed, so the frequency is less defined. The OH stretch of a carboxylic acid is easily recognizable because of how broad it is. Note that it starts at about 3500 and goes all the way down to about 2200. That is the OH. This is the C double bond O, and that would be the C single bond O. If you want to go back and remember, that peak at 2200 reciprocal centimeters corresponds to a C-C triple bond. So we can identify structural features, C-C single bonds, C-C double bonds, CHs, all from this particular spectrum. Lastly, we have the ester. And the ester is a combination of the C double bond O, the C single bond O, that we will see here at 1700, here at about 1200 or higher. But in addition, it makes a special peak, maybe a little peak that you might otherwise ignore, that indicates that it's not just a carboxylic acid because there's no giant peak here, but this little peak can indicate that these things are connected to make an ester.